Hey guys, today we're taking a look at biconditional statements. Now, a biconditional statement is just that. Bi, remember, is the prefix for to. So really what we have here is two conditional statements, both the original conditional and its converse. Now, biconditional statements are statements that have the clause if and only if. All right, so the notation for a biconditional statement using our P and our Q goes like this. P with the double-sided arrow Q. That stands for P if and only if Q. Now, you might be thinking I made a little typo here. This IFF is actually an abbreviation for this clause if and only if. And if and only if you're a math pro, you can use that clause. All right. So let's jump into a few examples. It says, write the conditional statement below as its converse, then as its biconditional. We're going to start off by identifying the P and the Q parts of our conditional statements here. So it says, if a triangle is an equilateral triangle, then it has three congruent sides. So I'm going to single underline my P statement, double underline my Q statement. Now, if I want to write this converse, remember the converse, I have to switch those two. So I'm going to start off by saying if a triangle has three congruent sides, and I'm going to abbreviate here as much as possible just to shorten up our video, then the triangle is equilateral. So there's the converse of that statement. Notice I switched my P and my Q. Now the biconditional of that statement takes both the if and the then and removes them from the statement. And I'm going to write now a triangle is equilateral, and then I'm going to insert my if and only if clause in the middle of my two statements P and Q. So we'll start off by saying a triangle is equilateral. Now I'm going to insert my if and only if. That's it, only. And now I'm going to insert my Q statement. All right, so I read here, now here is my biconditional. A triangle is equilateral if and only if it has three congruent sides. Now you should always make your sentences grammatically correct so that they're understandable. Let's try this next example. Your iPad insurance is valid if you keep the case on it. So notice now that my if comes at the middle of the sentence. So here is my P statement or my hypothesis. And my conclusion is then your iPad insurance is valid. Now to write the converse, remember we're switching the if and the then. So we're going to say if your iPad insurance is valid, then, and now we're going to finish it up with the P part of our statement here, then you kept the case on it. Whoops, we're going to make this correct here. All right, there we go. Now to write the biconditional, remember we're going to take the if and the then out of this, and we're going to insert our if and only if. Well, again, we don't have a then piece, so we're just going to take out the if, and we're going to write your iPad insurance is valid if and only if, and now we're going to abbreviate here, if and only if you keep your cover on. All right, so those are some examples of biconditional statements. Let's jump into our next example where we're asked to show if a biconditional statement is true. Now remember, biconditional, there are two conditional statements. In order for a biconditional statement to be true, both the conditional statement and its converse need to be true themselves. So you have to consider both cases. So example 3 says a rectangle has sides 12 and 25 if and only if its area is 300 centimeters. So I circled our if and only if clause to indicate where our statements are broken up. Here is our P statement, and our Q statement would be its area is 300. So if I want to consider the original conditional, that is P implies Q, I would read it as if a rectangle's side lengths are 12 by 25, then its area is 300. Now remember, the area of a rectangle is length times width, so if I take 12 and multiply it by 25, I do get 300. So this original conditional statement is true. However, if I switch it around now and I write Q arrow P, in other words the converse statement, then that would read if a rectangle's area is 300 centimeters squared, then its sides are 12 by 25. So in other words, I have to have a rectangle here where my area is 300 and the only two side combinations I can have are 12 and 25. Well, that's not true because I could have the side combination of 10 and 30. If I had if I had a rectangle that had sides 10 and 30, that would give me an area of 300 as well, but that would not be a rectangle that has sides 12 and 25. Therefore, this is an example of a counterexample in which we've proven that this statement, Q implies P, is false. And because it's false, we have to say this whole biconditional is false as well. All right, let's try the next example. Two angles are complementary if and only if they sum up to be 90 degrees. So again, here's my P statement, my Q statement. Let's test and see if P implies Q is true. If two angles are complementary, then they add to be 90. Yes, that is true because complementary means that they add to 90. Now let's take the converse of that. Q implies P. If two angles sum to 90, then they are complementary. Yes, that is also true. So for example 4, I cannot come up with a counterexample, and therefore this biconditional is a true statement. All right, next example says two angles are supplementary if and only if they form a linear pair. So we'll make this my P and my Q, and let's evaluate the truth of P implies Q. If two angles are supplementary, then they form a linear pair. Is this true or false? Well, I can come up with two angles that are supplementary, such as this angle here, 130, and this angle here, let's say it's 50 degrees. These guys are supplementary because they add to equal 180, but they don't form a linear pair. So this is my counterexample that proves this biconditional statement is false.